Not even close to the end, it's just beginning. Life is getting lighter while the days are getting brighter, yeah. And it's a good, I won't even worry anymore. Took all my cares, still can kick them all out the door.
Welcome everybody, good afternoon. Hope you're having a good show today. As Sean just said, my name is Bob Smith. I'm the Senior Vice President of Marketing and Business Development for Uniquify. We're a Silicon Valley-based company. We do a lot of SOC design work for our customers. Been at it for about 8 years, and about 4 years ago we embarked on a program to develop DDR IP because a lot of our customers were telling us, we were looking at these SOC designs and 90% of them needed to talk to SDRAM. So we decided we have a good idea on how to do DDR IP, and I'm going to talk about that today, this innovation we had. Uniquify, just because I really don't going to spend much time on the company. We're about 100 people, and as I mentioned, we're in Silicon Valley. So today I'm going to talk about adaptive DDR. And, what does that mean? When you say adaptive, I've had a lot of people at our booth say, what do you mean by adaptive? So we'll cover that. So if you think about designing an SOC, usually if you're talking to a design team, they're, we have a schedule to meet. I've got power, strict power requirements. I got to fit in a certain area. It needs to perform at some speed. But if you think about it, if your SOC has DDR on the outside, that becomes really critical, because if you can't read and write to memory, you can't do much else. And depending on where that device ends up in some kind of a system, if there's a problem with the DDR, there's a problem with the system, and frankly, if it's bad enough, you don't have a product anymore. You've got a big problem. So the point here is that the DDR interface is really, really important. So if we look at, okay, so we design a DDR, right? We design the interface and we say, wow, we were very careful. We think we thought of everything. But the reality is there's kind of two things we're fighting here when we design it. One is static, what I call static variation. So this is just the fact that manufacturing isn't perfect. If you make 1 million SOCs, every one of them is going to be a little bit different than the one next to it, than the one next to it. I mean, it might be, so small it's hard to measure, but there's a bell curve, right? And so no two devices are alike. And then you have the added problem, and this, by the way, this is not just the SOC, but it's your package, it's the external DRAM, it's the die, it's everything. And then you've got a whole other problem here, which is the dynamic, which is how is and where is this system being used? And is it in a server room with all kinds of nice refrigeration? Is it in somebody's closet that doesn't have any ventilation and they just close the door and forget about it and the closet warms up by 30 degrees? So there's we call this the dynamic, and so that's also could be dependent on the application. I mean, actually, a given system can also have dynamic excursions due to kind of the software load on the processor and so forth. So the reason this is critical to DDR is there's very little timing margin to play with. And so by the time we get to DDR4, our allowable timing margin is down just around 300 picoseconds, meaning that when your design is done, you better be within that 300 picosecond window across every condition you could think of, whether the product is out in the desert, whether it's in, it's buried under the ice somewhere. The point is that, and maybe you're making 1 million of them, so you better make sure that it works with all the other parts that it's connected to. So one of the big issues with DDR, getting the DDR system to work really well, is solving what we call the round-trip timing problem. And this is, the round-trip timing is the time it takes from when you issue a read command saying, okay, I want to go read something from my external memory, to the time that you actually get the data and the DQS or the SDRAM clock coming back. And now you have an issue to deal with. And the issue is, what is the relationship of that clock and the data that's associated with it to your system clock? And it turns out you would think, well, gee, isn't it all synchronous? Well, in reality, there is quite a bit of latency, and of course you've got, you're sending signals out over, perhaps across a board or other substrate. You've got, delays in the package itself. So it turns out that, when you're looking at this problem, what you're trying to figure out is how much latency, how many, clock cycles have gone by on my system clock since I issued the read, the latency, and what is the actual phase relationship of the edges. And solving that problem is typically done on the bench when, in the past, the SOC comes back, the engineers will go through lots and lots of samples, and they'll measure under different conditions, what does the delay look like and the phase relationship, and how much do I need to compensate for it typically using delay registers in the PHY. Very manual process. And it's difficult to predict, especially when you consider, what's going to happen out in the real world. So if you imagine here that after measuring a lot of different samples, we kind of pick this as our operating point. But later we find out that I have some systems out in the field that are maybe, let's say, getting too hot for whatever reason. They're jammed in a closet somewhere. Okay, all of a sudden here, our window's shifted, and now our operating point is just right outside of it. So I'm starting to get memory misses, memory problems. Not good. Not good. I'm going to wander back over here. So the innovation that Uniquify came up with was, look, we can never possibly predict every situation, every environment, every combination of parts that are going to be in the system. So rather than try to guess at it or model it, so broad that we throw away all the performance, why don't we build some circuitry into the PHY that actually measures, for this die, this package, this board, this SDR, measures this timing and precisely measures it down to a few picoseconds. Use that information then to program these registers on the fly and automatically center the window. Center right in the middle of the window, the timing. And this is actually what we call adaptive IP. We call it self-calibrating logic. And by that we mean the part calibrates itself to the environment it's in. And in fact, we announced this just about 2 years ago. More recently, about a year ago, we announced we have a number of customers now using what we call dynamic SCL, which is running SCL during system operation. We've got consumer product companies very interested in this because, their products end up all over the world in different environments. And the concept is the same, except now every few seconds you run this very fast hardware calibration. And even as your timing window is moving around, you're recentering the timing in the interface. So, instead of having this problem here where I have one fixed operating point, my operating point is actually moving and it's tracking the system. So there's some other benefits that actually come with this, and it's great to talk about, okay, it's nice you added some hardware, but actually because we've added this hardware, we completely eliminate the need for a FIFO for domain, basically for solving this clock domain crossing problem. And that gives us the smallest PHY on the market. We also have the lowest latency PHY. We're about 2.5 to 3 clock cycles, less latency than a typical FIFO-based PHY. And actually low power operation because there's just a bunch of circuitry associated with the PHY that we don't need to have there. It is fully automated. This actually runs in hardware. It's not software. It's actually dedicated small amount of hardware, and it's actually a hardware algorithm that runs. Simply give it a signal, write a command from the controller, and away it goes. The other thing I'll point out is the system bring up is phenomenally fast. Most of the customers I've talked to when they get that SOC back, they get that DDR interface up in less than half a day. Because again, they're not having to sit there on the bench and try all kinds of different combinations. They program and they say, go run this self-calibrating logic routine, and it will go off and find the optimal point for that interface. So in terms of, what do we offer to our customers and through ChipEstimate, basically we're pretty much covering all the bases, DDR2, 3, and 4, and LPDDR2 and 3. We're fully DFI compliant, so that means a lot of our customers will have their own, perhaps they have their own controller that they've designed. Perhaps they've had licensed one from somebody else. If it's DFI, we can talk to it. We're in production. You can see all the nodes there. We've got a number of designs out there in volume production now at 28. And again, we supply the controller, the PHY. This special circuitry is part of our PHY. It's not an add-on or an option. It's there, and if you choose not to use it, you don't need to use it, but it's there. And then we have a wide selection of IOs. So at this point, that's kind of my brief introduction to what we're doing. Are there any questions? Yes. Okay.
Questions right here.
Oh, here we go.
Oh, sorry. Yeah. Oh, no problem. My first question is, let us say right now there's a chip which is already in the design phase and we can't put your IP inside the SOC. Is there any way we can take this IP and put it on a validation board?
Is there any way you could put it on a validation board? Well, you would have to build it
Off
into.
chip.
Yeah, you would probably need to build it into some kind of small test chip or something.
Right.
Yeah.
Okay. Has anybody done that?
Not that I know of. I think it would be a little bit tricky. I could see potentially how it could be quite tricky. I'm thinking about the interface between the test
Right.
chip and your chip. How late are you in the design cycle?
Yeah, it's left the door, so.
Okay. It's out of the barn. Okay, we're not going to get it back.
Okay.
That's the only way I can think of would be to do it on some kind of a test chip like that.
Okay. And the second question is, does it come up with any automatic vectors for production?
As a matter of fact, we have at least one customer I know that's using the SCL to actually do at-speed testing on their
Okay.
production stuff, and they actually use that vehicle to test it
Okay.
because it's a pretty good indicator of pass-fail.
Okay. Thank you.
Oh, you're welcome.
Any other questions?
Thinking a free T-shirt here. These good questions, right,
yeah.
Sean?
Yes.
Okay.
And you I think someone asked, it might have been me yesterday, I can't remember,
Yeah.
after the DAC party, was going beyond 28.
Yeah.
nanometer.
Oh, absolutely. Yeah.
Okay.
I mean, we're doing a lot of design work at 28. We're actually got some stuff going on at 20, and we've got one partner we're talking a lot about 14 nanometer to right now. That'll be very exciting. That's not quite here yet, but very exciting what we'll be able to do in those processes.
Everybody get the ticket, raffle ticket? Thank you very much. And I can get you an extra ticket or a T-shirt. Your choice. Okay. What, you just want another T-shirt? Oh, yeah, sure. Why not? Ladies and gentlemen, Mr. Bob Smith right here. Thank you so much, Bob.